Good afternoon, everyone. I'm so excited to be here. The abstract talks about 2 methods for easing video consumption. We'll see if I actually get through both of them, okay? Depends how many questions you ask. So let me start by giving you a little bit of info about Yahoo Labs. You have flyers on the tables. Pay special attention to the WebScope flyers. So Yahoo Labs is about 200 researchers in 5 locations: Haifa, London, New York, San Francisco, and Sunnyvale. We work on search, advertising, mail, and content, including video and text content on the web. We are actively involved in the research community, and we make impact on product daily. And in particular today, I'm talking about video, so keep a close eye on Yahoo's Tumblr and the Yahoo Labs Tumblr, because we'll be making some announcements about new products in the next few weeks that are driven entirely by the video technology coming out of Yahoo Labs, some of which you may like to use, actually. So we provide data to researchers through our WebScope program. All you need is an EDU address, and both of the things that I hope to get to today have WebScope data sets associated with them that you can download and use yourself. We also have a great intern program. We have 50 to 75 interns each summer, and if you're interested, you should apply last month. But we're still interviewing, so definitely if you're interested, apply immediately. Don't wait till January or February or March, and that goes not just for us, but for all the industrial research labs. We make grants to faculty collaborators, and one of the great things about coming to Georgia Tech is we have several faculty here that we either have grants with now or had collaborations with in the past. So we're really excited about that, and we host faculty visitors. So if any of you who are faculty or postdocs come to the New York City area, feel free to stop by our office. We have food, you can give a talk, you can talk with some of our researchers. All right. The work that I'm going to be talking about today comes from these 2 groups that I currently manage. The group in the top, the top is the text understanding and discourse and summarization group, and the 4 smiling faces in the front are our summer interns from this past summer. And the group in the bottom is the video understanding and summarization group. And the smiling faces to the left, third from the left and right, are their summer interns from this past summer. So these are the people whose work I'm going to be talking about today. Now let me talk a little bit about video. Video is increasingly prevalent on the web. Okay. Users currently, as of 2015, spend more time every day, almost 2 hours, interacting with video online than they do on social networks. This is a change. This is a crossing point versus last year. Over 100 hours of video are uploaded to YouTube every minute. At Yahoo, in our New York City office, we produce over 100 hours of original video content each week, and that's just in one of our locations. By 2019, 75% of all internet traffic will be video, according to Cisco, and in that year, more bits of video will cross the network every 5 minutes than an individual could watch in 5 million years. So the web is increasingly becoming the web of video, not the web of text content. One area where tech companies are still trying to make an impact is that online video is insufficiently monetized. That is, we don't make enough money from it compared to how much we spend to produce and distribute it. So if any of you have interesting ideas about that, we are actively working on ways to monetize video. Now, it so happens that I prefer to read things than watch them. How many of you prefer to read versus watch? How many of you prefer to watch versus read? Okay. How many of you have taken a class where at least some of the lectures were online in the form of video? How many of you watched that video at its regular real-time speed? There you go. This is one of the things that we like to do about video. Scan it quickly, preview it, get summaries of it. Okay. So that's one of the things that I'm going to be talking about today. How many of you remember going to that thing called a library? Okay. How many of you have ever used a card index? Okay, so actually a surprisingly large number. I'm kind of stunned. So back in the day, if you wanted to read a book, maybe someone would tell you about the book, social networking, collaborative filtering. Otherwise, if there was a topic that you were interested in or some information that you wanted, you would go to the library and you would use this thing called a card index that contained metadata about books, their publishers, their authors, their keywords, and their categories. You would search through that, and then you would go find the book on the shelf, and you could preview the book by reading, say, the back cover or the table of contents. And then if you wanted to find the actual piece of information in the book, you would flip through it or find it in the index or something, right? Nowadays, if you want to find some information in a book, you go to a website that has the electronic versions of those books and you do a keyword search. That's literally, you can search inside a book, you can go straight to the page you want, you can skim the pages of the book, everything is awesome. With video, we still live in the library age. So if you want to find a video, maybe a friend sends it to you, that's great, collaborative filtering is an awesome thing. Or if you actually want to search for something in a video, for example, last week's Saturday Night Live, the skit where Donald Trump's hair was in focus, then you would go to an index, a keyword search engine, where you would search through the metadata of the video, the publishers, the category, the keywords. You would find the video, and then you would maybe look at the front cover, that is the description. And then if you wanted to find the actual skit, you would have to scan through the video until you found it, because we don't have indexes for videos. Since we know that video is accounting already for more than half of web content, how can it be that half of the content in the web is essentially locked away in black boxes like books used to be in a library? This is a crazy world, right? So what would you like to do with video? Here are some things that I would like to do with video. I would like to be able to search through, for, and within videos. And that's part of the talk. It was originally the first part of this talk, but hearing what some of you are interested in, I've swapped it for the second half of the talk, so we may get to that at the end. I would like to be able to preview videos or see them quicker, because I can't be hassled to spend time on them the way they are. And I'm going to talk about that first. I would like ranking and recommendation for videos, and that is technology that currently exists on a collaborative filtering basis, but it would be nice to be able to do it over the content of the videos. In order to do that, we have to really develop understanding of videos, and that a lot of people are working on that, including people at Yahoo Labs. And I would like, of course, to make money off my videos, and in order to do that, I also need to understand the videos. So I'm going to be talking today first about previewing, viewing, and previewing summaries of videos, and second, if we have time, about searching through videos, both of which allow us to open up the black boxes that videos are and get out of the library mindset and more into the World Wide Web mindset. So, currently, if you want to preview a video, there are two ways that you can do that. If it's a movie, like a really professionally produced video, maybe they give you a teaser. Teasers are awesome, but they are designed to conceal more than they reveal, right? So I won't call them summaries, I'll just call them teasers. For the vast majority of video on the web, including the vast majority that Yahoo produces, the sort of summary that you might see is a thumbnail. And if you're lucky, that thumbnail was selected carefully by a human. And if you're unlucky, it's a random frame from the video. Could be anything. So if you are looking at user-generated video, for example, the video of the whale that totally landed on the kayak last month, a randomly selected frame might just show you the kayak on the ocean. That's not at all a representative thumbnail or summary of that video. What we're trying to do is create representative summaries of videos, both in the form of animated GIFs and in the form of video, shorter forms of those videos, which is what I'm going to be talking about today. You might want to preview a video to decide if you want to see it, or you might want to preview a video to just get the gist of it. And the sorts of summaries that I'm talking about today are get the gist of it. The animated GIFs are for if you want to decide if you want to see it. All right. Now, traditional video summarization is frame-based, as I said. A lot of that work comes from the TrekVid community, where the game is essentially surveillance. There's 24 hours a day of a green field, and some poor guy has to sit and watch it, and then the game is to figure out when the green camouflage man gets into the green field. Okay. So it's okay just to get every 1,000th frame, because hopefully the green man is in the green field for more than 1,000 frames, and you can do this. These videos are great for those applications, but they totally lack coherence, and they're not at all user-friendly. Right? You as a consumer would hate to watch such a summary of a video. In 2014, which is only last year, a group of researchers released a data set of user-generated videos with manually created summaries, and that data set is called SumMe. The first author on that paper was an intern in our group this past summer. Recently, researchers have explored using web images to create summaries of videos instead of just frames from within the videos. And that's also a technique that we're going to be using today. That work was published in 2013. So what we're going to be looking at is summarization of for users, regular users like you and I, of content that is aimed for users, using web images and video and frames from the video. So the question is, how can we automatically create user-friendly, informative previews or gists of videos? We could use the video metadata and the thumbnails, but metadata is often lacking from videos. They don't have the equivalent of the back cover of the book at all. And thumbnails, you could be picking any sort of frame from the video for a thumbnail. Video summaries should provide the main points of the video, but video producers often won't produce them. So that's why we need a way to do this automatically. So this work was published at CVPR earlier this year, and the data set from it is available on WebScope, so you can download it and use it as well. Okay. What kind of summaries do we want to generate? We want to generate summaries that are relevant to the video. They shouldn't be random, okay? And we want to generate summaries that are coherent, unlike the frame-based summaries used in surveillance videos. So we're going to do a title-oriented summary. Most videos do have a title. And because the video is title-oriented, that will make the summary topical. And we want to do a shot-based summary. Shot-based means multiple frames in a row instead of just single frames. That will help us to get coherence. Okay. All right. So a brief word about data representation, since some of you may be very familiar with computer vision, and some of you, like me, may not. And because a lot of work that's being done this year and in the past couple of years, especially with images, uses only the pixels as representations. But here we're not using only the pixels, which is the lowest level of representation of a video. We're also not trying to do deep video understanding in this particular project. So we're not trying to identify the objects and actions and scenes. We're at an intermediate level of representation with functional features. So the way that we represent a frame or an image is using a 1600 dimensional feature vector comprising color features, RGB and HSV color features, pyramid of Hogg to identify shapes, gist for scene info, and dense sift for local appearance info. So these are all intermediate representation features, and there are libraries like OpenCV that will allow you to compute them on images. So the representation of an image or a video frame is one of these vectors, and the representation for the whole video is a matrix of these vectors in order of the frames. Okay? All right. So here's the system that we built. You have a video and you have a title. What you do with the title is we do web image crawling from the title, and what we do with the video is we segment it into shots. And then the web images and the shots and the frames in the shots all participate in the next three steps, which are canonical visual concept learning, and that's where I'm going to spend the bulk of my time because it's a really interesting method that you may be able to apply for other things, followed by shot importance scoring and actual summary generation. And what you get out is a shorter version of the video. And the budget that we're using here is 15% of the length of the original video. So you really save a lot of time if you just watch the summary. Let me talk about the web image crawling first. Let's say the title of the video was Kitten Needs the Human. Okay, this is some kind of YouTube video. The world is full of kittens needing things. So the first step that we do is stop word and special character removal. And what you would get out from there is tokens like kitten needs human, and the is gone. Then we do synonym expansion, and you get kitten and cat needing human. And then we do n-gram expansion, and you get kitten needs human, cat needs human, kitten needs, cat needs, etc., all the way down to 1 grams, kitten needs, and human. Each of these is a query that we input into the Yahoo image search engine, and what we get out is a lot of pictures. And some of those pictures are going to be of kittens, and some of those pictures are going to be of humans, and some of those pictures are going to be of bread. Why? Needing. Okay, now, the bread pictures are not relevant to the video, but they come out of the title search. And so we'll come back to the bread pictures later. At the same time that we're doing that, what we're doing on the video is shot segmentation. For shot segmentation, we cast the problem as a multiple change point detection problem. So remember that each frame in the video is represented as a vector. We can plot those vectors in space and draw a curve between them. Then we're looking at change points for change points on that curve. There is an optimal solution, an optimal exact solution using dynamic programming, but it's crazy slow. So we use a convex formulation approximate solution. We're trying to, the first half of that there is measuring the reconstruction error to reconstruct the shot, the frames in the shot. And the second half measures the total variation amongst the frames in the video. And that parameter lambda there controls the relative importance between the reconstruction error and the total variation. So this function incorporates a notion of representativeness of frames, so it assigns low scores to similar looking but less representative frames, and helps us to remove redundant information in the eventual summary. Okay, so now we have our video split into shots, and we also have a bunch of web images that correspond to terms in the title of the video. Now we're going to take these images and these video frames, and we're going to build a joint representation of the importance of the video frames with respect to the images on the web that are relevant to that video, okay? So I'm going to give you the math first, and then I'm going to show you a pretty picture, and then I'm going to make an analogy to text summarization for those of you who've done NLP like me. So the goal here is to learn a dictionary of visual patterns, which we're going to call Z, where these visual patterns are shared jointly between the web images and the frames in the video. Okay. Each of the frames in the video and each of the web images in the web images should be well approximated by some of the patterns in the dictionary. And each of the patterns in the dictionary should be well approximated by a combination of the frames in the video and the web images, but neither of them separately, just the joint combination. Okay. The way that we do this is through a technique that we call co-archetypal analysis. We formulate it as an optimization problem. We're trying to find an optimal solution set from a weighted combination of the frames in the video, the web images, and the two of them together. So the first part of that function there is optimizing for the video factorization, the second for the web image factorization, and the third one, which is really important, is the two of them together. And we use that factor gamma to weight them. So it controls to what extent we enforce the joint constraint. And in this work we just set it to 1. Okay. Now, the latent variables, right, we call those co-archetypes of the frames in the video and the images because they jointly model the two together. In the process of finding it, we call co-archetypal analysis. There was some work in the 90s on a method called archetypal analysis, and we use that as one of our comparison systems. The power here comes from the fact that web images tell you what everybody takes pictures of, and the video frames tell you what's here, and you want things that are kind of surprising or unusual here, as well as in the web images. Okay. So compared to archetypal analysis, co-archetypal analysis does this joint modeling, not either of them separately. And among other things, this allows us to effectively deal with noise and variance, noise from the web images. So those bread pictures won't occur in the video frame. So although they happen quite a bit in the web images, they won't occur in the video frame, so the joint model won't contain them. That's the noise. It also allows us to deal with variance. The video might contain a lot of concepts in it. We don't know how many. I can't say ahead of time that it's 10 or 16 or 24. This will just take as many as it needs to produce the right dictionary. Okay? All right, so now for the pretty picture. Just to give you another approach at the co-archetypal analysis. We have this input video, and there are terms from the title, and we get web images from them. So we have our video frames here and our web images there. And some of our web images contain kittens and humans, and some of our video frames contain kittens and humans, and some of our web images are of bread, and some of our video frames are of chair that the human is sitting in, right? So what we're going to get in the joint representation is the kitten and the human, and what we're going to be leaving out is the bread and the chair. Okay? All right. Now, let me finish telling you about the system, and then I'll make an analogy to text summarization. Now we have this dictionary, Z, which tells us things that happen in our video frames and in our web images that are related to the title of the video. We need to use this dictionary to compute the importance scores of frames in each of the shots, and then we're going to compute the importance scores of the shots themselves. All right, so the frame importance scores are, the score of the ith frame is the score of the frame with respect to the dictionary Z. Okay, so we cluster the frames with respect to the elements of the dictionary, and then we compute the distance from each frame to the closest element of the dictionary, and that's the score of that frame. And then we take the shot importance scores. I don't know what happened there. Come back. Okay, the shot importance scores are computed as the average of the frame importance scores for the frames in the shot. So that's very easy, we just average. And then how we construct the summary. We have our length L, which is 15% of the length of the original video. We solve the 0-1 knapsack. Okay, I can just say that and show you the math, but I'm going to tell you what we do. You find the shots that are most highly weighted with respect to the video and aren't redundant with respect to each other, and put those shots in the summary until we hit our budget length. So it's a very simple, very efficient method. All right. Now, I'm not classically a video person, as you could probably tell from my bio. However, I have done some work on text summarization, so for me it makes some sense to try to think about how this video summarization approach is similar to text summarization. In text summarization, our basic units are sentences. In this approach to video summarization, our basic units are shots, not frames, shots. Now, a shot is like a sentence because it's comprised of frames if we pretend that frames are like words. Okay, so let's pretend that frames are like words, and then shots are like sentences. How we score sentences for text summarization is using relevance and redundancy. Relevance with respect to the document and redundancy with respect to the summary so far. How we're going to be scoring our shots for our video summarization with respect to relevance. How relevant is this shot, the frames in this shot, to the video? And redundancy, how redundant are the frames, is this shot with respect to the summary so far? It's exactly the same. How we compute relevance in text summarization is using TF-IDF, which is a way to measure how interesting a word is. And then we average the TF-IDF, or compute cosine, between sentences. How we're going to compute relevance and redundancy for the video summarization is the co-archetypal analysis of frames with respect to web images. So it's something like TF-IDF. It's not quite like TF-IDF, but it's very similar. And similarly with respect to redundancy, we're doing something like TF-IDF, only here it's co-archetypal analysis with respect to the other frames in our video as computed through our dictionary, which folds in the web images. So now we have a video summarization approach that is very analogous to text summarization, in at least my mind. So if you've worked on text summarization, that's the analogy. Now, of course, you want to see how good are these summaries, right? All right. So we developed a new data set called TVSum50. We collected 50 videos from the web, 5 each, from 10 categories from TrekVid consumer video. Okay. We made sure that the videos weren't too long or too short, so between 2 and 10 minutes. We made sure that they had a Creative Commons license so anybody could use them, so you can use them. And we made sure that they each contained more than a single shot, so like the camera cut and then something else happened. And that they have a visually descriptive title, because a lot of people don't write visually descriptive titles. So this comprises 3.5 hours of video in total. And for each video, we did the title web image search, and we collected up to 200 images from the Yahoo image search engine. Okay. And we obtained ground truth importance scores using Mechanical Turk. Now, if I said to you, here's a video, right? Construct for me the most important pieces of this video, you would probably, and you were being paid, I don't know, $1 to do this, you would probably take the first 15 seconds of the video and say, I'm done, right? Or you might go through it from the beginning until you had found pieces that were representative and then say you were done. This is the early effect. There's a different term for it in the paper, but this just means that people lean early in their attention. We wanted to avoid that in collecting our ground truth summaries. So here's how we did it. We asked the Turker to read the title of the video. Then we asked them to watch the whole video all the way through from beginning to end. They couldn't pause it, they couldn't stop it. Right? Then we showed them 2-second segments of the video, and we asked them to say for each of those 2-second segments how important that segment was with respect to the video. Okay. For a video that's 8 minutes long, that's going to be crazy, right? Your Turker is going to come and find you in your house and hang you up by your feet. So we clustered the shots using k-means clustering using visual similarity. So you would get clusters of shots, clusters of these 2-second shots by how visually similar they were. And that way, if the Turker thought that one of the clusters was completely unimportant, they could just drag all of those shots into the unimportant bin. And we also didn't want them to label every shot as important or every shot as unimportant. So we asked them to only put 1 to 5% of the shots in the very important bin, all the way down to up to 60% of the shots in the rest of the data, in the unimportant bin. And we also muted the video, so there's no audio here. There's nothing going on in the language channel. We got 20 Turkers to do this for each video, and we computed Cronbach's alpha to get an assessment of how much the raters agreed, and it was very high. It was 0.81. And this is a different way of constructing ground truth summaries than were used in the SumMe data set from 2014. And we think this is more accurate because it avoids the recency, the earliness effect. And because if 2 shots are very visually similar, the Turker would probably put them in a similar bin. Whereas before, you might get one segment that's very similar to another, and the 2 end up in really different bins, and that's difficult for a summarizer to deal with. Again, this data is available on WebScope, and you too can use it. And now I'm going to show you some examples of the summaries that our system produced. Okay. I'm actually going to go here. So this video is a little weird. All right. This is Barbie playing the violin, and it's totally silent because we muted the audio. And it's called Katie's Performance. And I don't know, maybe a friend sent this to me, and now I'm already bored because there's a lot of zooming in and zooming out on Barbie and Ken, and I don't know. Oh, you can't see it. Well, how do I make that happen? I can see it. Okay, let me pause Barbie and Ken. Maybe I need some technical assistance here.
Do a mirror. So if you press Command and F1, that will mirror your screen.
Okay, let's see if that works.
It will show everything.
Yay, okay. Here's Barbie. Okay, can everybody see Barbie now? Yes. Okay, I'm gonna let it go for 30 seconds and then I want a hands up if you're bored. Who's bored? Okay, very good. So we do two things with this video. We construct these summary GIFs, which you should ignore because I'm not talking about how we do that here. And we construct this summary video using the technology that I just described, okay? So I'm going to pause the original video and show you the summary. Now, the original video, I believe, is roughly 8 minutes long. Okay. You're probably still bored, but at least the zooming in is going by faster, right? There's less of each zoom, clipping to the next bit. Okay. Now I want to show you another example. This is a sports video. I have no idea what this guy is doing. Let's look at the GIF first. He's wildly excited about his car, his motorcycle on the beach, okay? So already I know something about this video. This original video is over 10 minutes long. Here he is doing something. I don't know what. He's looking at his motorcycle. What? You're already bored? We're only 6 seconds in. Okay. It might be a motorcycle, it might be a car. I think he's looking at his car and then he eventually rides his motorcycle. Now we're 10 seconds in. Okay. There's some sport, I can skip forward, which is how you would normally try to do this, right? And then we try it again. There he is, now he's riding down the beach. But maybe I missed something really important. Maybe I missed the bit where he jumped into the water, right? So let's see what actually happens in this video. This is a shorter form of the video. There he is, like, oh, and here's my car. And here's my motorcycle. So at least the introductory bit is going by faster, right? You're still getting the gist of the video. Like if the whole point of this video is lost on you, then it's still going to be lost on you, but at least it's going by faster. Look, we're only 19 seconds in and already he's put his helmet on. So this is good. Let me show you one more. This is an animated video. This technology works regardless. So here's the summary GIF. Does anybody know what this cartoon is? Because I don't watch the cartoon. Somebody, Clarence. Okay. Okay, so this is Clarence. We know somebody who's not going to be bored. Okay. So there's a lot of stuff happening in here. I think this must be a preview of the whole movie or a TV show or something. This technology also works on video trailers, movie trailers. It doesn't matter. The input is a video, the output is a shorter one. Okay. So there you go. This one actually goes on for a long time. It goes on for like 22 minutes. I think it's the whole episode. Here's the summary. It's going by a lot faster. We're sort of skipping chunks. Yep. Okay. So, and you could repeat this. You could run it on 10% of the video or 5% of the video, or you could nest the summaries until they're shorter and shorter. This whole summary is about 2 minutes long. The original video is 11 minutes long. Okay. So you can see that we're getting something more coherent than if we just took every nth frame or stitched shots together using k-means clustering. And in case you don't believe me, let me go back and tell you about the evaluation. Make sure everybody's still seeing. Okay. So we compared many systems. We tried shot sampling. Shot sampling involves just segment the video into shots, And then either we take every nth shot or we take random shots and we stitch them together for a summary. You would hope that that would work pretty badly for most videos. We tried shot clustering, which is like frame clustering approaches, only it's shot clustering. We k-means cluster the frames and compute the distance of each shot to the centroid of the biggest clusters as the average of its frame distances. And then we keep adding the most important shot to our summary until we hit our budget and we're done. And we tried two kinds of clustering, k-means clustering and spectral clustering. Those are our baselines. We then compared with several other recently published systems. One is a web image prior. In the web image prior, we develop our clusters by taking 100 web images from images for this video and another class for all the images from other videos, not for this video. And then we compute the frame level distances, the shot level distances, and construct the summary. We tried archetypal analysis, which is when we just develop our archetypes from the video frames, and another approach where we just develop our archetypes from the web images. So this is no co-archetypal, but we still have this notion of a dictionary. Okay. And then we tried an approach called Live Light, which was published very recently last year, where the key idea is that you remove redundant shots over time. So you remove the most redundant shot, then the second most redundant shot until you're down to your budget limit. Okay, now Live Light is state of the art. Okay. It also uses a different method for shot importance scoring than we use, so we compared the two methods for shot importance scoring. Now here are our results. First on our data set, TV Sum 50, you can see that the baselines in fact do very badly. These results are measured using Rouge Meteor, those kinds of things, overlap with our human constructed summaries. So the baselines do very badly. Live Light does quite well. And the web image priors and the archetypal, individual, not co-archetypal, also do very badly. And our co-archetypal method does very well. In fact, for 7 of the 10 categories in the TV Sum data set, the co-archetypal method beat every other method. For 3 of the categories, Live Light beat co-archetypal or was equivalent to it. The co-archetypal analysis performance is statistically significantly different from that of all systems except Live Light. We also did a comparison using SumMe, which is the only previous user video that with summaries available to us. And the first 2 with stars, those results are from the previous reported work, and the next 3 results we computed. And you can see here again that the co-archetypal analysis outperforms all the other methods. All right. When we used Live Light's method for importance scoring with all of these methods, we got worse results than when we used our method for importance scoring. So the method for importance scoring is also important. So let me conclude. Titles provide useful cues to video content. However, web images mined using title keywords can contain noise and variance. That's where we got the bread. And the frames in the video may also contain variance. Co-archetypal analysis is very useful to learn canonical visual representations, which among other things can be used for summarization. Now, we used it for summarization. You might have some other ideas about how to use it. And co-archetypal analysis is better than archetypal analysis because it can deal with the noise and the variation in the input. And finally, the importance scoring function also matters. So one of the things that we're looking at now is how we can use co-archetypal analysis for concept learning, object detection, action recognition, etc. Another thing that we're looking at is using additional metadata to improve the summarization. And some of you might have some ideas about how we could do that. We could use some of the higher level representations of objects and actions and scenes, for instance, to better distinguish between shots and so on. But you can try out this technology soon, if you keep an eye on our lab's website, and you can download the data now. All right? So that's the first half of the talk. So now I don't have to watch the whole video. I can just watch 15% of the video or 15% of 15% of the video. Already I'm a lot happier. But some of those videos had speech. Like I'm pretty sure that Katie the Barbie was playing the violin, or somebody was playing the violin. And maybe I would like to understand also or use the language in the video. Okay. So in particular, I want to use the language in the video to search through the video. And as you know, right now when you go to search through a video, mostly you can only search using the metadata. Okay. There is one exception. I think it's this month or last month. YouTube added this hidden field where if you supply like, I think it's :cc or something, it will also search through the closed captions that are provided on YouTube videos. But that's the exception. But let's imagine that I could search through the video content. Oftentimes, the news or the daily show has multiple segments. Maybe I'm only interested in one segment. I should be able to find that segment based on the language used in that segment. I would also perhaps like to look through the content of the video using the visual information, but that's a whole different thing that I'm not going to talk about today. The New York Times had an article last month where they were talking specifically about this open problem of searching through video content online and how it's something that needs to be done, and many major content providers are working on it. There has, in fact, been some previous work on this. The Shoah Foundation for Visual History and Education conducted interviews with Holocaust survivors. They manually closed captioned and aligned and indexed and analyzed those interviews, and you can go and search through that content online. This was done starting in 1999, and obviously they were dealing with many people who have heavily accented speech and may have speech difficulties, or because they're elderly, have creaky voice, so speech recognition isn't going to work very well, so they did it all manually. More recently, there was a system called Empirical. Empirical did large-scale content analysis through automatic transcription of the language of the speech in a video, as well as some computer vision techniques that were going along in a parallel but completely separate track. And so that you could, for example, search the evening news for that bit where Barack Obama was interviewed and find the bit where Barack Obama was interviewed or Barack Obama was mentioned. Empirical was a great research project, but there are many important legal and commercial constraints around the use of closed captions and consumer-produced video, for example, from NBC or CNN. So Empirical didn't end up as a product. But it was the closest thing that I can find to what I would like to actually use. Okay. Now, what I would like is to index the language content in the video so that I can search through it, right? And there was a law passed in 2010 called the CVAA, and I understand Georgia Tech has a big center on accessibility research. So how many of you here know what the CVAA is? Communications and Video Accessibility Act of 2010. Thank you. It increases the mandate for the provision of closed captioning on video, which means that more and more providers are actually passing on the closed captions that are attached to their videos or providing them if they didn't. Now, this is an incredibly useful source because unlike speech recognition, it's fairly high accuracy and plays, thanks to HTML5, in most web-based players. So people increasingly put the closed captions with their video content on the web. This is all great, and actually Yahoo closed captions are videos. However, closed captions are expensive to produce, so we would like to make extra use of them, for example, for indexing. And it turns out that humans are not really terrific at time aligning speech with transcriptions because we can only perceive up to like 1/3 of a second, and you want to do it much more fine-grained than that. Furthermore, search engine operators won't index text that is not visible in the page. Why? Because there was a time when people who wanted to spam or spoof you would stick all kinds of text in the page. We've all heard about Google bombing, stuff like that. So search engine operators won't index text that's not in the page, and we can't get Yahoo, for example, to display closed captions in the page because they're not very pretty. They're not very well formatted, especially when they're done through an automatic process. So we need to convert the closed captions into a pretty transcript so we can put it in the page so the search engine operators will index it so I can search inside the video. Okay, this is a very selfish project. So this work was published this year in Interspeech, and the goal here is to generate a formatted text from raw text. The three pieces to that are insert punctuation, capitalize, and put paragraph breaks so that I'm looking at a big old blob of nothing text, right? And in addition to indexing, we can use that language content then to help with shot segmentation, to identify salient objects in videos, and to make videos more skimmable. All right, so this is the method that we use. The closed captions or speech recognition output come in. We do caption alignment to align the closed captions with the speech. As a side effect, we get much better alignments of closed captions with speech than a human could produce. Then we do punctuation insertion, capitalization, and paragraph splitting, and what comes out is a formatted transcript, which isn't perfect, but is much better than the raw text. So let me first talk about the caption alignment. And unlike the first part of this talk, everything in the second part you could do, because we're using all open source software, so I'll mention the software as I go. We're using Sphinx for this, so we take the video and extract the audio. And we take the captions, or the raw text, and we generate pronunciations for each word using a grapheme to phoneme model from Sphinx. We then do sequence alignment of those phoneme level, those are the basic sound units like and b, with respect to the speech using the Sphinx aligner. You can download it, you can use it, and what we get out is VTT, which is a closed caption format with very fine-grained sub-second level alignments. All right, so now we have something, text that's aligned with the speech, and you're going, well, you had text in the beginning, why didn't you just use that? Well, we didn't just use that because we want to use the acoustic and prosodic information in the speech for punctuation. For example, when people pause a long time, maybe they mean a full stop. Okay, so that's why we need the alignment. So now we're going to do punctuation insertion, and our goal is to predict when to insert a punctuation between tokens and which punctuation type to insert. And we assessed using several sentence ending punctuations, period, exclamation mark, and question mark, as well as a couple of internal punctuations, hyphen, comma, and of course, the ever-present none. Okay. We would hate to insert a punctuation between every pair of words. And although punctuation is just the first step in the process, we hypothesized that its impact would be large because it is necessary for sentence initial capitalization, and because only when you know the sentences can you decide where to insert the paragraph boundaries. All right, you may think, why don't we just insert punctuation when there's pauses? But actually, over half of the time when there's a pause, there shouldn't be any punctuation, and over roughly a half of the time when there's a punctuation, there is no pause, because people don't all speak like a news broadcaster. I, for example, am deliberately right now not speaking like a news broadcaster, so I'm not stopping at the end of a sentence, and I am stopping in the middle. Okay, so this is the kind of speech that we have. All right. So we experimented with several systems for punctuation insertion. The first system uses what's called a trigram language model. So we take punctuated text and we say, for every 3 word tokens, is there a punctuation somewhere in there? And then we use that to predict when to put punctuation in unpunctuated text. The second baseline, based on the previous slide, uses silence. If the silence is really short, no punctuation. If the silence is intermediate, comma. If the silence is long, full stop. This one can only do 3 types of punctuation, none, comma, and full stop. We have a speech-only system that uses a random forest trained on acoustic and prosodic features from the aligned speech. We use the system OpenSmile to get these features. There's over 2,000 of them, and they are what's called functional features. So we look at the speech signal, and we say, is the pitch changing? Is the speaking rate changing? Is there some voiced here, like ha versus not voiced? Is the energy changing? Is the duration changing? All of these things, and we construct features over those. The text-only system uses a conditional random field with a window of 7, so much bigger than our language model. So we're looking at a sliding window of 7 tokens. At each token, we're looking at the part of speech in the token, and we're saying, should a punctuation go here? But otherwise, it's a lot like the language model. And we have an ensemble system that takes the output from the speech and text systems and trains a linear regression, a logistic regression on the predicted labels and confidence scores from those 2 input systems. All right. After we do punctuation insertion, we do capitalization. For this, we use machine translation system called Moses. We're essentially translating from uncapitalized text to capitalized text. That sounds a little weird, but it works. It works pretty well. And for paragraph insertion, we totally misuse the ancient system text tiling. Who knows about text tiling? Paper by Marty Hurst from the early 90s. Text tiling was for topic segmentation of text. We use it to split on paragraph breaks when the topics change. Okay. All right. So the data that we have is Yahoo screen videos from November through February. And these videos will soon be available on Webscope, and you can download them and use them, and the closed captions will come with them. Okay. The categories include Saturday Night Live, finance, sports, and Yahoo News Trending Now. They were manually closed captioned. And the manual closed captions do contain capitalizations and punctuations, but they don't contain paragraph breaks. Since that time, Yahoo uses automatic, semi-automatic closed captioning. So the semi-automatic closed captions don't contain capitalizations and punctuations, and that's where our system would come in. It would insert them. But it's great that we had these several months of data that we could train on and use to test. So we have over 500 videos here split into training. Dev used to train the ensemble method and test. Okay, and here are the results for punctuation insertion. We assess the performance using word error rate, which tells us if we inserted a punctuation in the right place, and F1, which is a balanced combination of precision and recall, which tells us if we even guess the punctuation right. Okay. The two baselines have a fairly high word error rate and a fairly low F1. This is bad. The text-only system has a word error rate half that of baseline 1, which is good, and a much higher F1. The speech-only system has a word error rate slightly higher than the text-only system, which isn't great, and an exactly the same F1. And the ensemble method performs slightly better than the text-only method. Okay? Only slightly, but again, we hypothesized that we would have a big downstream impact. So now let's look at the capitalization performance, which again we evaluated using our manually provided input closed captions. We computed capitalization using the output from the text-only punctuation insertion system as input, the speech-only, and the ensemble method. And here you can really see the impact of correct, better punctuation insertion, because there's a huge impact, a huge difference in accuracy of capitalization between the speech-only system and the ensemble system. Okay. Remember, we have no gold standard data for punctuation, for paragraph insertion, but we were interested in how easy it is for people to read the transcripts output by our system. So I'm going to skip this slide. So we conducted a readability evaluation. We automatically pre-processed our transcripts to remove some funny artifacts output by the machine translation system, such as white space between could and nt, okay, and to normalize numbers. We showed these to Turkers. We showed them the output from the speech-only system, the ensemble system, the text-only system, and the closed captions just dumped in the page. And we told them these transcripts were produced by computer programs, and we asked them to rate each transcript from 1 best to 3 worst. So they saw 3 transcripts, and they were asked to use the whole range if they could, but they could assign 2 transcripts to the same number if they needed to. Each of our test videos was posted as a hit on Mechanical Turk with 7 Turkers assigned to it. And a system was designated a winner for that video if at least 4 of the Turkers gave that system the rank of 1, best. Okay? Okay, and here you can see the results. Our speech-only system had a macro averaged rank of 2.17, which was the lowest of the 3. It had 6 winners and 15 losers. Okay. The text-only system had a macro averaged rank of 1.92. It had 6 winners also and only 4 losers. So it did better than the speech-only system. However, the ensemble system, with a macro averaged rank of 1.87, had 10 winners and only 1 loser. So it was the clear winner here. Not that these transcripts are perfect, and I'll show you some examples, but that they're a lot better than just dumping the captions into the page. And with more training data, we could do a lot better. So let me show you some examples of these. Okay, make sure you can all see. All right, so this is a sports video. Yahoo News, and I have no idea who Jim McElwain is. Some sports guy. Who knows who he is? Okay, that's him, I guess. This is the caption output, okay, from the manually provided closed captions. So you've got capitalization and punctuation, but no paragraph breaks. This is the raw text, which would be the output from our current closed caption provider. There's no capitalization, there's no punctuation, there's no paragraph breaks. It's basically unreadable. And this is well-formatted text from our speech-based system. You can see there are some issues with capitalization, but we're getting some sentence final punctuations right. We're skipping some of them, but we're getting some of them. And this is one of those artifacts that we removed when we showed them to Turkers. We would get rid of the space there. And here it's all 1 paragraph. Now if I go back, that's the speech-only system. And if I show you the ensemble system's output, we're working on it. There you go. The ensemble system's output actually has 3 paragraphs instead of 1. And those 3 paragraphs make a kind of sense. This is an introduction paragraph. This is about defense. And this is about offense. Okay. So you can see it's not perfect. There's still some issues. Colorado State, McElwain. But it's much better than the raw text. Right? Everyone prefers this one over that one? Okay. Yes?
So the caption, this is a Yahoo produced video.
Yes.
So the closed caption track was generated by someone at Yahoo Sports.
The closed caption track was provided by a closed captioning vendor.
Okay. But it was higher quality than a lot would be because it came from a professional vendor.
Yes, but the closed captions are produced semi-automatically, so they're not formatted, capitalized, punctuated. Yeah, the accuracy is high.
Accuracy is
Their accuracy is fairly high. Yeah. So let me conclude this portion of the talk. Okay. The Turkers praised the highly ranked transcript variants for the flow of the language. They condemned some of the low-ranked variations for being too chopped up, okay, if there were too many paragraphs, which happens sometimes, for being one big block of text if there were too few, which happened a lot with the speech-only model, for missing capitalizations, which they noticed. They didn't really complain about the punctuation, but they did complain about the missing speaker changes, and we did nothing to indicate speaker changes. So if somebody's interviewing somebody else, you might get paragraph breaks there, but we wouldn't even say person A, person B. So we conclude that punctuation is useful for improving the readability of transcripts, that prosodic information and text information work well together, and that given a raw transcription and speech signal, we can produce a sort of readable transcript. In the future, we're looking at speaker changes, as well as acoustic events like closing doors, slamming doors, clapping, laughter, and music, which the Turkers also noticed when a song was playing. And these acoustic events are what throw off the alignment in our system as well. So what I've talked about here is two projects. One where we use computer science technology to make videos shorter, and one where we use computer science technology to make videos easier to index. What's next for video? If you're a PhD student or thinking of doing a PhD, what should you do a PhD on? Well, I have a suggestion for you. I think that right now the research community is doing a lot of work with joint visual and language representations for image processing, and that the next obvious step is to extend those representations for video processing. A video is harder because it's bigger, but there are some nice features to it. The temporal order of the frames gives you a really important clue, and because you have animation, because it's video, you can do action detection, and then you can use the temporal information and the actions to constrain what you're doing, whether it's summarization or video or high-level video understanding. So if you're going to do a PhD in something to do with video, may I suggest that you look at high-level content understanding for video and joint language and visual representations for video, and you would really be breaking new ground. As far as I can tell, there's only one video data set available for the research community that even has both of those sources of input, and that's a media data set from Media Eval. And with that, if you break new ground in that area with deep learning or whatever technology, co-archetypal analysis, whatever technology you use, you would not only be able to publish many excellent papers and make a lot of friends, but it's very of profound interest to many tech and media companies, including Yahoo. So it's not entirely selflessly that I suggest this. It would also make me as a user very happy if I had other ways to interact with video content than just to sit and watch it. So that's my suggestion. Do something with joint language and visual representations of video. And I would look forward to seeing that, and it would work well with some of the HRI and HCI work that's being done at Georgia Tech as well. So thank you very much for listening to me.
Okay, so we have time for 1 to 2 questions from the audience.
Yes.
So the context of my question is when you were talking about the cat needing a person, you make multiple queries and you put them together into one Google query to get a set of results to dig data from.
Okay.
So my question is, do you know where to find Google's specification for their query language? I have not been able to find that anywhere.
The question is about web image search and the way that we query web images with the title keywords to get images for our video summarization paradigm. So we extracted these n-grams over the input title, and we used each of those as a query. So we conducted multiple queries, and the particular image search API that we were using was the Yahoo Image API. You could search Flickr, for instance. We would be happy to talk with you about searching Flickr or the Yahoo Image API for using those query terms.
So they documented their query language?
Yes, and if you send me an email, I'll put you in touch with someone. Okay?
What?
If you send me an email, which I'm on the web, I'll put you in touch with someone who can send you the API.
For the Yahoo?
Yeah.
Oh, so it's not publicly available?
I don't think so. Well, I'm sure that there is one publicly available. Our APIs go in and out of availability, but we could send you the very latest one.
Okay.
Yeah. Next question. Yes.
I'm studying MSHCI, and I wanted to, you said in the end of your talk that there's a place for people like me to work with you.
Yes.
But all the lecture was about math and descriptors. So can you tell a bit more about our opportunities?
Yes, of course. So Yahoo hires HCI people in several different capacities. One is as designers, working to design the user interfaces for our future mobile applications and user interactions. Another is to conduct usability studies and design usability studies. We do usability studies all the time. For a new Yahoo product that is coming out soon that is built on the Yahoo video technology, we conducted many user studies around what people care about when they're choosing and watching videos, what is visually interesting to them, and how their eyes track across videos, all of which may be interesting to you. So we have HCI researchers both within labs and in a whole separate organization at Yahoo called Usability or Human Factors that work tightly with the engineering and product groups to really formulate the new applications at Yahoo. We also have a separate group, the Yahoo Accessibility Lab, who go in and test every technology to make sure that it meets our accessibility guidelines before we release it. So we have lots of scope for HCI people at Yahoo. And I'm in touch with people. I know people both in the usability group, in the accessibility lab, and in labs who are HCI people. And if you're interested, send me an email.
Okay, well, thank you. So let's give a round of applause again to Amanda.
Thank you.